Everyone, and welcome to the AI seminar once again. I am Ratul, a new PhD student in computer science, and today I am going to talk about a research conducted by the researchers of Google DeepMind about on the theoretical limitations of embedding-based retrieval. So these are the topics that I am going to cover today. At first, I will briefly discuss about what is information retrieval, what are the categories, how they work, and their limitations. After that, we'll get into the details of that research paper, what is their findings, their theoretical findings, their empirical findings, and what alternatives they are suggesting, and how it actually affected my own research. So, what is information retrieval? Suppose you have a system with a large collection of resource or you can say documents, and you are giving a query to that system asking that to find top relevant results, and it gives you the results. Okay, so just think about the Google search, GPT model, etc., etc. So this whole process is called information retrieval because we're actually extracting information from these systems using our questions or query. So when we search for something information retrieval information retrieval model, it helps find the most relevant documents and ranks them based on our query. So it's not only gives us information only, it actually sorts or ranks this information from most relevant to least relevant documents and gives us the results. So there are many ways that you can use for categorize information retrieval. But if we consider the factor semantic understanding, so based on this factor, we can mainly categorize the information retrieval into two main categories. The first one is sparse retrieval, which actually doesn't understand semantic meanings. And the second one is dense retrieval, or you can say for this particular presentation, single vector embeddings, which actually understands the semantic meanings. So let's get introduced with the sparse retrieval. It's a very traditional technique. So it is the foundation or of traditional search engines like Google or Bing or Yahoo, you can say, and it only focuses on exact word matching. That means, for example, it can differentiate between the word like fast and speedy, although their semantic meanings are the same. That's because it has no semantic understanding. In sparse retrieval, documents and queries. Queries are our questions and documents that what inside our database both are represented using sparse vectors based on word frequencies or term importance. So we'll be looking at the examples. So some common techniques are TF-IDF that are term frequency and inverse document frequency, and BM25, which is a more advanced version of TF-IDF. So what is TF-IDF? It is a statistic which is used to evaluate how important a word is in a document relative to the entire corpus. So the term frequency means how often a term appears in a single document, and inverse document frequency refers how rare or common the term is across all the documents. So if a term appears in many documents, the IDF is lower. It means it's a very generic or insignificant term. So the term frequency represents how important that term is for the document only, but there can be like generic words like small, large, calculation, model, powerful, that might have appeared in the document for so many times, but these are not significant words. So how will we nullify their impact? So, okay, so before getting into this, nullifying their impact, just see how we can calculate the term frequency. So it's the ratio of ratio of how many times that term is appearing in the document D divided by total number of terms in that document. But I already said that there can be many generic words inside that document that will have the like high term frequency. So we have to nullify them. So to mitigate their impact, we use inverse document frequency or IDF, which uses a logarithm to decrease the weight of words that appear very frequently across all the documents. So it's the total number of documents in the whole corpus and the number of documents which contain that specific term. Now let's see an example. Terms that appear frequently in a document but infrequently across the whole corpus are considered important because the insignificant words appear across all the documents, but some terms that is significant for a single document may not likely appear in all the documents. For example, let's say our query is a sports car, and our first document is I love sports cars. For this query, sports cars, the document 1 matches both the terms very well, that is sports and car. But for the document 2, cars are fast, it only matches with the word cars. So document 1 gets higher score because both sports and cars are important. So the TF-IDF score is very high for that. Now another technique of sparse retrieval, the BM25, it stands for best matching 25 because it is the 25th version of a ranking algorithm developed by some researchers from London in the 90s. So it's an extension of TF-IDF that improves upon it with term saturation. So what does the term saturation mean? Term saturation. So term saturation means if some particular term is appearing very frequently in a document, the importance of that particular term doesn't increase linearly. So at some point, it saturates that term so that it impact doesn't get like linearly increased. So the score of BM25 is just the summation of all the terms and their particular IDF and TF product. For example, a similar example, let's say our query is fast sports car, and our document is I love sports cars, they are really fast. One thing to notice here, the first sports cars are appearing in two different contexts, in two different sentences. But for the document 2, sports cars are fast and popular. So here the sports and cars and fast appearing very closely. That doesn't mean it will be a higher impact. The result is document 1 might score higher because the query terms match in different contexts. So it's important. In document 2, the word fast doesn't get extra weight just because it appears once in a small cluster. So that's the functionality of BM25. So there are some limitations of this kind of sparse retrieval techniques. The first one, we can say they can't understand any context or synonyms, paraphrase, or any kind of semantic meanings. And that's a huge disadvantage of this kind of retrieval. And they are very bad, very, very bad at reasoning tasks. And also, there can be like variable vocabulary mismatch, like sports car and fast vehicle are the similar phrases. But it will be missed by this kind of retrieval because they use exact word matching. Okay, so the dense retrieval comes into play. It's a modern technique actually. So dense retrieval is driven by deep learning models that understands the semantic meaning of queries and documents, and it actually understands context and meaning if the words don't exactly matches. So what it uses? It uses dense embeddings, excuse me, dense vector embeddings to represent the documents and queries. Actually, we will be talking about single vector embeddings. Okay, some examples are bar, T5, or the GPT models. So what is embeddings? So embedding is just a representational technique. So it is a way to represent data as numbers in a vector. So it doesn't actually store raw text. We turn it into numbers that capture its meaning. For example, like the word cat, dog, and car, if we want to represent these three words into vector embeddings using three features. The first feature, it is a hypothetical example. So you can assume this feature is like the tail size. So the cat has a tail, and the dog has also a tail, but the car doesn't have any. So the score of these two is higher than the car. And for the second feature, you can say is the size. So the cat has the least size, and dog is a little bit bigger than cats, and the car is the biggest. So these are hypothetical like scores. Here, the number of features is the dimension of the embeddings. Okay, so you can see here cat and dog vectors are very close. That means both are animals, while car is far. So we have already talked about the dimension. So it's the fixed length that we use to represent any raw text or any raw data. Think of dimension as the number of features used to describe its meaning. So in embeddings, dimensions could be like 300, 768, which is very common, even 1500, and even the most biggest embeddings nowadays are above 4000. So cat in a 3D embedding, we can represent it using three individual numbers in a single vector representation. And if we convert it or want to represent it in 768 dimensional embeddings, the representation may look like this. Now, let's see how the embedding-based retrieval works. Suppose we have three documents in our data set, like I love cats, I bought a car, dogs are loyal, and we are representing these three documents in three individual features. So our dimension number is 3 here. Now, if a user enters a query like cute pet animal, so what it does, it will convert the query itself to the embedding representation, and after that it will compare with all the documents in our data set and compute its similarity. It might be using dot product or cosine similarity. So using this similarity, it gives us the results, the top results, and as we mentioned earlier, it will give us rankings, the most similar to least similar. So for that particular query, it's also a hypothetical example. So this document, I love cats, might score the highest, which is very close. Then after that, dogs, and after that, car, which is like very far. So if we want to retrieve the top 2 documents from the data set, these first 2 will be retrieved. So that's how the information retrieval works actually. So, but what's the problem? It understands semantics, but there is a inherent problem inside that. So, single vector representation, although it's a dominant method used by neural search models, it actually utilizes the geometry. So, the model finds relevance by calculating how geometrically close the query vector U is to the document vector using dot product or cosine similarity. So, just imagine you are trying to summarize a very large document into a single vector of like maybe 100,000 dimension. So, actually people kind of knew it has some limitations. So, the paper from Google DeepMind, which provides a formal basis for a limitation in single vector retrieval systems, but before getting into the details, it's important to clarify what the paper actually proves. It says this isn't about models' inability to understand language. It's about the it's not about semantics. It's about combinatorics. So it says the single vector paradigm has fundamental limitations. The capacity of these models is restricted by the size, that is the dimension size of the embedding, even in realistic settings with extremely simple queries. So it doesn't necessarily that like it's performing very poorly because the queries are very hard. It's not like that. So if I want to tell you the whole thing in one line, it says for a fixed embedding dimension D, there exists top k combinations of documents that cannot be returned. So it's very important to understand what does it mean by top k combinations and top k results. For a single query, the top k results are the like if you want to retrieve top 10, it will just give you the ranking of first top 10. But here, the top k combinations of documents mean across all possible queries, which sets of documents could never appear in the top k. So let's break it down. Suppose in the whole dataset we have only 3 documents: cats, dogs, and cars. So we want to get all possible combination of the 3 documents, and we want, let's say we want to take the first 2. So what will be our combinations? Like 3, C, 2. So the combinations will be either cats and dogs, cats and cars, or dogs and cars. That's all total 3 of them, of size 2 actually. But what's the problem actually? So let's say we are representing all the documents in 2-dimensional space, because we can't like if I put an example of 3-dimensional embeddings and put another example of 4-dimensional embeddings, we can't like visualize them. So let's say our embedding space is 2-dimensional. So we represent all the 3 documents: cats, dogs, and cars. Here, cats, dogs, and cars in this 2-dimensional space. That is our dimension 1. That is our dimension 2. So it's also a hypothetical. So let's say cats is placed here, dogs is here, and cars, which is like not very similar to these cats and dogs, this is residing far away from them. Okay. So, for example, our query 1 is who likes pets or likes pets. That's it, simple. So if we also convert this query into 2-dimensional embedding, it's likely that it will be placed surrounding of dogs and cats. Let's say, for example, it is residing here. So if you want to retrieve the first two most similar documents from this embedding space, it will give you the values, the documents cats and dogs only. And another example is likes vehicles, and if we convert these embeddings into embeddings, it will be residing nearby the cars. So if we want to retrieve the first two top documents from this embedding space, it will give you cars, and the second similar dogs. But what if we want this combination, cats and cars? In no way you can be able to get the results cats and cats and cars. Wherever you want to place it, you can think of that. You can't get cats and cars together in this two-dimensional space. So we can get cars and dogs, but it's impossible to get cars and cats together. But if we increase our embedding dimension, let's say it's a three-dimensional space, then it will be possible to retrieve all the kinds of combinations of documents. So that's a very simple example to understand what this paper is actually trying to say. So our theoretical limits of this embedding-based retrieval, nowadays search tasks are now demanding the models to represent any possible relevant definition for any query. So this requires models to capture a huge number of combinations. So actually that's our challenge. So our you can say that's our demand. So we want any possible combination of documents for any query. But what's stopping us? The constraint, the dimension D. So the length of the list of numbers, that's the dimension of D, so dimension of embeddings, limits the total number of unique combinations, which we already saw in the previous example. So they have used a math link. They took an off-the-shelf theory, the sign rank from communication complexity theory, to prove that the bottleneck here is the dimension. And our simple requirement is to capture a complex set of answers. The embeddings dimension D must be large enough to keep all those combinations mathematically distinct. So we'll be seeing that. So let's just simplify their theoretical proof and understand that easily. So the formalization is just assume we have a set of m number of queries and n number of documents. And for each of the queries, we are representing it into a real number embedding of dimension D. And for the document also, we are also converting it into embeddings. So after that, we are concatenating all the query vectors. So we are getting a dimension of, for each of the query, D, and number of queries is m. So if we concatenate it, so the concatenating vector will be like D into m, and similarly for all the documents it will be D into n. So our score matrix, or we say that query document relevance, or the QRELS matrix, it will be the transpose of U and V. So if we transpose this vector, so these two are getting reversed, so it is becoming m into D. And if we do matrix multiplication, we are getting this QRELS matrix of size m into n. So here the document 1 and query 1, value is, if this is like 1, it represents they are very relevant, and for Q2 and D2, if it's 0, it's representing this has a very less relevance. So we just simplified the Q-rails matrix. So here the documents are D1, D2, D3, and there are just 2 queries. So the as I said, the zeros represent there are very less relevance, and ones represent there is a very high relevance. That's our Q-rails matrix. And then from this Q-rails matrix, we will be getting the sign matrix. So if you switch all the zeros to -1, you get a sign matrix with only +1 and -1. And from this sign matrix, you will be able to calculate sign rank. So what is the sign rank? Actually, the researchers borrowed the results from other researchers who already studied the sign rank of some matrices. Since computing the sign rank directly is very hard, they used these known results as the shortcuts. So what does the sign rank say? The sign rank is, it's our actually the lower bound. The sign rank is the minimum number of dimensions needed so that we can reconstruct or reproduce the Q-rails matrix. In another word, just see this, if the sign rank is 2, that means we need at least 2-dimensional embeddings to reproduce the Q-rails matrix, so that we can get all possible combination of document for any query. Obviously, the K, that means the number of documents you want to retrieve will be fixed. And if our embeddings are only 1-dimensional, we can never be able to represent this relevance pattern correctly. So what is the consequences? So there's a minimum number of dimensions, which is the sign rank, we need for embeddings to represent all query document relationships correctly, and no universal small embedding works for all retrieval problems. That's very important. And if we have a data set and the ground truth, we can measure how hard a data set is by checking how many dimensions are needed to fit it. So they also have done an empirical proof, which is called the best case failure. I'll tell you what does that mean. So they tested the absolute best case scenario called free embedding optimization. Free embedding means the vectors are randomly initialized as unit vector embedding. So that's why they are calling it free. And there is no complex model like BART or anything. The vectors themselves are the model here. So the document and query vectors are directly optimized to solve the answer key, that is Q-rails matrix, perfectly without the constraint of real language. So they didn't use any kind of language models, so that their constraint don't get involved in that. So embeddings are directly optimized on the test set itself. So you can say they overfitted this embedding model. So but that's not a problem, because the goal here is to answer a question is this task even possible to solve with a given embedding dimension D, and assuming the model is very perfect. So the test set was synthetically created for this experiment, and they generated a query for every possible combination of document 2. So this created a ground truth for a relevance matrix, the Q-rails matrix that the free embeddings were trained to solve. It's like, if I want to tell you very simply, it's like our, this example. So you are free to go anywhere and try to retrieve cats and cars, but you know where the cars are residing, right? The cats is residing, but you can't get those two as your retrieved documents, even if you know their position. So that's the free embedding means. So they overfitted the free embeddings, even it can't solve the problem. Okay. So the finding, the critical n, is very important. So even in this perfect scenario, there is a critical point, we are calling it critical n, where the number of documents becomes too large for the fixed dimension d to solve the task perfectly. That means if we fix the k value, that is the number of documents we want to retrieve, and we fix the dimension d, so then we will be able to get a critical n number, which is the largest possible combination of documents that we can retrieve. After that, beyond that, we will not able to get the results. This experiment shows a clear relationship actually. Here, the k is fixed at 2. That means we want to get the first 2 documents. As the embedding dimension gets bigger, the critical n increases. That means the factor here is the d. So the model can handle a much larger number of documents before it actually fails. This proves that the dimension d of the embedding fundamentally limits the capacity of this retrieval task that it can solve. And remember, even under ideal conditions. So one thing to notice here, this curve is actually a third degree polynomial. So it increases the number of documents that we can be able to retrieve correctly is increasing with respect to d, but it's third degree polynomial. It's not exponential. So what if it was exponential? If it was exponential, the curve would look like this. So at some point for d, we will get very high number value for the critical n, so that we can retrieve a very large number of combinations of documents. But it's not the case here. So what they found, for a fixed embedding dimension d, 512, the critical n is somewhere like 500,000 documents. And for the largest possible embedding dimensions, that is 4096, the total number of combinations of documents is 250 million documents. But in modern search, web search problems, there can be billions of documents. So this shows empirically the limiting factor is d. So now comes the limit data set, or you can say the most potent contribution of this paper. So it is engineered to have a very high sign rank actually. So to create a realistic natural language data set that is simple for a human but is designed to hit the theoretical sign rank limitation. So they are deliberately trying to hit the wall of the embedding models. So the design of the dataset is very simple. Like they are using this simple text like who likes apples, who likes quokkas, and etc. The complexity limit dataset is constructed to test all possible combinations of relevant documents for a given set of queries. That means the queryal pattern will be very dense, not sparse. This structure forces the model to encode the maximum required complexity actually. So the core of this dataset is a set of 1035 queries, and those are designed to retrieve every possible pair of from a pool of 46 documents. Yeah. So two constraints they have maintained: users shouldn't have too many attributes, and thus keeping the document short. So they are keeping the document very short, and each query should only ask for one item to keep the task simple. So it's a very simple data set. Even in this simple data set, the state-of-the-art single vector embedding models like Gemini Embed, Grid LM, E5 Mistral are performing very poorly, scoring around less than 20% recall at 100. But in contrast, the Colbert, that is multi-vector, and BM25 high dimensional sparse are performing significantly better here. You can see from the figure. So the problem isn't about the task itself, so it's about the tool we are using. For the first two recalls, we can see the effect of D, but in the last graph of recall at 100, it shows that for bigger dimension D, from here to here, it's giving more number of relevant documents. So we can come to the conclusion that dimension actually matters, and model performance depends actually on the embedding dimension D, and models with larger dimensions generally perform better. They also verified if the domain shift is the issue here. So, but what actually the domain shift is? Domain shift happens when you train a model with one kind of data and you are testing it with like another kind of data. So you may think the model might perform poorly because the data distribution has maybe changed. But that's not the case here. They created a synthetic training set and a test set and fine-tuned the state-of-the-art embedding models on the training set and tested it on the test set. So see here, the training models on a limit data set, so the training models on a limit training set did not significantly improve the performance. So you can see this is the performance of our train set, and if we train it using the test set, the performance gets like very improved. So the performance only improved if they trained directly on the test set. That means overfitting. This proves that the data set was hard for the model, not because they are unfamiliar to the model. So our professor already told you in yesterday's email that this paper has sparked some significant discussion in the research community. So let's just read some random comments from different social media. They're actually very mixed and diverse. So Mr. Konstantin G, a technology executive from Wells Fargo, he thinks that single vector embeddings are not the silver bullet, particularly for research. Seems like he has a very little hope remaining in this kind of retrieval. And another AI entrepreneur commented on his post, on his LinkedIn post. He explains, okay, so he explains the issue this way: people mistakenly think of vector search as a simple two-step process. First, you create a fixed embedding of the document, and second, you compare your query to that static or unchanging vector. But he proposes a more dynamic approach. For every search, the language model should combine the text plus query to create a new and unique embedding on the fly. So I actually don't understand clearly what he's trying to say, but I believe he's proposing something very good. So this comment is from another side. He's trying to say, like, most representations that compress information for retrieval are very lossy. And for example, embeddings are a form of lossy compression because we are representing each document, large documents, into one single vector embeddings. So similar to the no free lunch theorem, no lossy compression method is universally better than another, since downstream tasks may depend on the specific information that gets lost. So therefore, the question is question is not which representation is perfect, but which representation is better aligned with the AI system. So because our AI system is evolving very rapidly, it will be like difficult to predict like what will be the limitation of the future works. And another comment from Reddit. So he's trying to say that what's the point in publishing this? We already knew that. But another guy opposes him, saying that, okay, but it is good to have a formal paper from a tech giant to help protect those developing RAG under or with unrealistic exceptions.
I think what the poll mentioned is a scenario that you are using the language as input for the ChatGPT or some other large language models. For example, if you want to ask what is closest to a cat, that sentence is in the format of text, right?
Yeah.
And you are using the large language model. The large language model is using the transformer to getting the answers from the weight. From the weight it has. It's not retrieving from a data set, unless you are using RAG, right? And it is different than than treating the sentence, finding the closest thing to a cat, using that sentence as a input to a database for information retrieval. Those are two different techniques, right? They can all be considered as information retrieval, but I think in this paper they only focus on the pure embedding and the embedding-based information retrieval. It's not related to how you normally ask ChatGPT.
Thank you. So what are the alternatives they are suggesting? So one of them is cross encoders or re-rankers. So instead of squeezing the meaning into one static vector, they evaluate the query and the candidate documents together and modeling their interactions directly. So they are combining the query and the document, and the result of this is much higher accuracy, scoring nearly like 100% perfect accuracy on the limit dataset, although at the cost of like extra computation and latency, obviously. And another limitation of this kind encoders is like they cannot be scaled very easily. One example is that I already said, the Gemini 2.5 Pro, which performed really good on the limit dataset. The second one is multi-vector models. So multi-vector models are like instead of one vector, multiple vectors per item. So what they are doing, they are kind of like breaking down the semantic meanings into pieces. So into several smaller, more specific semantic pieces, each with its own vector. So they are creating multiple vectors for a single item. These models perform greatly above the single vector ones on limit dataset. And one of the example that we previously saw is GT Modern Colbert here. And the last one is our old traditional sparse models. So it performs surprisingly well, often near perfect scores. The inherent dimensionality is very high, and it matches with lots of individual words or phrases actually, because it's a large system. But the limitation of sparse model is understanding semantics like complex instructions, and also they are very bad at reasoning, where keywords aren't obvious. So obviously embeddings handle reasoning tasks better, So it's absolutely a critical trade-off, we can say. How it actually affected my own research or our own research. So let me give you some description about our research project. So let's think about a research paper. So a research paper may cite 30, 40 or 50 other papers, but it's obvious that not all are closely related to the main content, because some references are cited like just for the definitions, background study, literature review, and etc. So you can like notice typically 3, 5 or 8 papers are the most relevant, especially those used in the like for benchmarks, like for in results, comparison analysis, and the sections like that. We actually calling this smaller set, the most important set of papers, as master set. So actually it is a citation recommendation system. So let's say this is our system, and if you want to like find out what will be your like the papers, most relevant papers that you want to cite for your manuscript. So you would give our system a manuscript. It can be half completed or full completed. It can already cited some papers. So what our system would do, it will suggest, it will give you an output of a master set. So it will suggest you some papers after like computing your manuscript. So for this project, we actually thought about the cybert and fine tuning it to make it perform better on the AI artificial intelligence type of papers. So we took around 133,000 of papers from different AI conferences, and we actually used these techniques, but the results are not that satisfactory. So that actually makes sense, because we're representing large documents into a single vector embeddings, which the cyber does. So we are now thinking of like some combined approach, which is very common recently. So that's how it affected actually. So in summary, the paper shows that vector embeddings face an inherent limits, but it's not like that we are just throwing it away. We just have to just keep in mind the limitations and think of our approach, like what would be the most suitable architecture for our specific tasks. So for requiring the full range of query complexity, the community should focus on alternative retrieval approaches such as cross encoders. We actually discussed about that, multi-vector models, to overcome the constraint of the single vector paradigm. So that's it. Thanks for your patience. If you have any questions, it will be appreciated.
I have a question. So can you go to the slide 25?
Yeah.
24. Yeah. So here, suppose Q2 with D2. So it's like there are not not relation like
Yeah.
Q2 with D2.
Yeah.
So
And we can determine this if we have the ground truth.
So okay. Okay. So if we don't have ground truth, then how we can deal those type of things?
The goal is not like determine if any unknown data set, like if you have any unknown ground truth of data set, the goal is not here to calculate how many number of embeddings we need to like reconstruct this. It's just a way to prove that there will be a limiting factor D. For proving that, they are like using this known data set actually.
I really like your example about the cat, dog, and the vehicle. It's very intuitive. When you introduced it, I was thinking in what circumstance you want to find, you want to have a query that is both relevant to the cat and the vehicle. But then after I thought about it, maybe you just want to ask what is the atom that is closest to both cat and the vehicle, right? That is a valid query. And in your example, you perfectly demonstrated that there's no way you can place the point of the query in the two-dimensional space that you can return the result of both the cat and the vehicle. I think so. I think that is a perfect example.
Thank you, Professor.
And regarding the takeaways, I'm still not sure how much if it affects what we use for information retrieval, because let's assume we are using BERT or SCI BERT. It has 768 dimensions, right? And according to the conclusions of this paper, as soon as you have less than 1.7 million documents, right?
Yeah.
The theoretically you can still technically have a embedding method that can perfectly return the results for any queries, right? But for our own application, we're trying to do the citation recommendation based on a citation data set, and we only have, I don't remember, 130
thousand, yeah.
Documents, right? That is much less than 1.7 million. But however, this is the limitation when we have the perfect embedding method.
Exactly,
right?
yeah.
So even the number of documents is much less than this. But we know for sure we don't have the perfect embedding method, and there's no way we can train the model, we can fine tune the model to be perfect. So we still don't know for sure how much it affects our results.
Yeah, that's true.
And regarding the alternatives, one thing I noticed is the option that interests me the most is the
multi-vector models, yeah.
Yeah, multi-vector model. I think it also makes sense to have a multi-vector representation that is also represented in a graph. For example, given a research article, instead of representing the article in one single embedding, you can have multiple vectors, but those multiple vectors are not, just the discrete vectors. They may have different relationships. Your query could be, I want to find the atom that is closest to both the cat and the vehicle, right? So you have the cat, you have the vehicle, and there's a relationship. The relationship is or and, right? It's a logic relationship. Yeah. And that is just for a one sentence query. Your query could be much more complicated. It could be the abstract of the article. It could be a very long document, right? And in those cases, there are a lot of information in the document, and instead of just having several discrete multi-vector representations, it may be better to represent the vectors in a graph, and you can if you can represent all the articles in the data set as graphs, you have thousands of graphs, right? You have hundreds of thousands of graphs, and you are doing a graph search in a graph data set. I think that is a very promising direction as well.
Yeah, for our research, yeah.
Yeah.
Any other questions?
I have one more question. So, have they think about anything like hybrid models, like incorporating sparse and dense both?
So they're very common nowadays. So I'm studying. So what will be
I'm questioning about their paper, like they mention about anything hybrid models, like what's the limitation of hybrid models?
I haven't seen that, but they just recommended it.
Yeah, I don't think it's very simple to combine both. Because in the industry, what I know is it is a very common practice that you want to use the PM25 on the very large data set first. For example, you want to retrieve the first 100, the top 100. Then you use the embedding-based method for finding the top 10 maybe. That is one way. But like Ratul has introduced, when you filter out the top 100, that didn't consider the thematics, right? If you search animal, you couldn't find something related to cat because the cat isn't. According to the vocabulary, it's not an animal, right? But semantically, the cat is an animal. But so in the first step, when you do the BM25, you already missed a lot of the correct results from the query. So yeah, that is the most common way of combining the sparse and the dense retrieval methods, and it may work for some applications, but theoretically it wouldn't. It's far from being perfect.
Yeah. What about I'm thinking about suppose taking sparse and dense both for the retrieving, but using weight like for sparse 50% weight